Hello, good morning everyone. So let's begin today's session. Today we are going to cover feature extraction and the most important and popular technique for feature extraction for dimensionality reduction is principal component analysis, that is popularly being known as PCA. In fact, we had an introduction to this concept. So we know what is feature extraction. So given n number of features, we are going to find out m number of features out of those n original features where m is less than n. But in contrast with feature selection, here we are not simply selecting the features from the original feature set. Instead, the original feature set is being transformed or projected into a new subspace with smaller dimension. So, given the feature set with n features, these feature extraction techniques are actually transforming the original feature set into n number of features, and we are going to come up with entirely new features. Those are obtained by the original one, right? We are going to make use of the projection or the transformation of the original features, and in our new feature set we'll be having m number of features. Those are less than the original number of features n. So whatever we are getting as the outcome of feature extraction, this is actually the function of the original feature set, right? Now, to do this, we are going to make use of the concept of projection. So we are going to project the original data onto a new space with few dimensions, right? So how to do that? Let us see one example in 2 dimensions so that we can understand it better. So what we have here is, we are having few samples in our data set, and these samples are denoted, or these samples are described two features x1 and x2. So here my feature vector x is having two features x1 and x2, right? So my original dimensionality of the feature set is R square, or it is two-dimensional feature space. And what I want is, I want to convert this two-dimensional feature space into one-dimensional feature space. I want to reduce the number of features. So for simplicity, we are having this example of converting 2D space into 1D space. Right? Now, how to do that? We are going to have such kind of a line or a vector. Right? Please remember, this is not a regression line, but this is a line wherein we are going to reduce or minimize the projection errors. Right? So let us assume that we are having this particular line. So what we are going to do next is, we are going to compute the projection error for this line. Now, how do we compute this projection error? We are going to drop the perpendicular from the instance in the feature space to this selected line. So see here, we are dropping the perpendiculars line from the instances, right? So these are the distances my instances from this projection line, right? So this is actually the error associated with every instance, right? As I stated, this is not the regression line. Whenever we compute the regression, we compute the mean square error, right? Here we are computing the projection error. If you remember, in case of regression, we try to compute the error like this vertical error from the line, regression line. But here we are not going to have this vertical error, but we are going to drop a perpendicular from this point instance to the projection line, right? And we are going to compute the errors. Right? Now, we come up with the errors. Now, this is not the only projection line that we may have. We may have several such projection lines. So let us assume that we are having this another projection line. So once again, what we are going to do is we are going to find out the projection error, right? So see here, from every instance, we are going to compute this perpendicular distance to the projection line, and this would form the error for this projection line, right? So this is how for such kinds of projection lines we are going to compute projection errors. And the essence is which projection line to be selected, right? So here we are going to find out a projection line or a vector onto which to project the data such that this projection line or this vector is minimizing the projection error, right? So the error that is computed for this green line and the error that has been computed for this red line, whichever error minimum, we are going to select that particular vector or that particular projection line to project our data, right? So this is with respect to a two-dimensional space, and we are converting this two-dimensional space to one-dimensional space. So we are finding out a vector in this space such that the projection error is minimum. Let us try to extend this concept to 3 dimensions, right? So here let us assume that we are having the data points and those are described with 3 features. So here my feature vector x is having 3 features, x1, x2 and x3, right? So I am having a 3-dimensional space, and what I want is I want to convert this 3-dimensional space into 2-dimensional. What does this mean? I want to reduce the number of features from 3 to 2. Let us assume. Okay. Now, see here what we are going to do. As I stated, the original feature space is 3 dimensions, having 3 dimensions, and we are going to convert this 3-dimensional space to 2D space. So, we are going to pick now 2 vectors in 2 dimensions, right? So, these 2 vectors are actually forming a plane, right? These 2 vectors are actually forming a plane. And what we are going to do next is, whichever are the points, those are described in 3D space, those points are being projected onto this 2-dimensional plane, right? So we are transforming 3D point into a 2D point, right? So this is how we are going to reduce the dimensionality from 3 dimensions to 2 dimensions. So in general, we are going to reduce from n dimensions to m dimensions, from n dimensions to m dimensions, where m is less than n. So if this is the case, and if we want to transform our feature space from n dimensions to m dimensions, then we need to find out m vectors onto which we are going to project the data, right? And we would like to find out such m vectors so as to minimize the projection error, right? So in the first case, here we are transforming from 2D to 1D, and we have selected this as our projection line or vector, right? So what we are going to do simply is we are going to project this point here on this line. See, what we are going to do, we are simply moving this point. We are going to project this point onto this line. This point gets projected here. This point almost having the same location, so this gets projected here. This instance get projected here, and this instance get projected here, right? So every instance that was described earlier with 2 features x1 and x2, now those points are lying on our vector or the projection line. So simply try to move this horizontally, right? So let us align this particular projection line horizontally. So if we try to relocate this line horizontally, then we may get something like this. So all those points are being projected on this line, right? And we are having all those points described with a single quantity. So we have converted our 2D space into 1D. 2D points are being converted into 1D. Fine. So let's see this another example with 3 dimensions. So what we have done here for 3 dimensions, we want to convert this 3D space to 2D space, right? So we have picked up 2 vectors, right? And along the direction of these 2 vectors, we are having this plane. And simply what we are going to do is the point in the 3 dimensions is being projected onto this plane, 2D plane. And this is how we are going to convert the 3D space into 2D. So in this case, every point in 3 dimensions is now been described with 2 features in 2 dimensions. Right? So this can be applied to any number of dimensions. Right? For simplicity, for the sake of understanding, I have demonstrated example converting to 2D. Right? So, in this scenario, if my original instance is described with x1, x2, x3, 3 features, now in 2 dimensions, the same instance can be described like z1, z2 having 2 features. Right? Now, the obvious question that you may have is how to do that, how to transform, how to find out these vectors. Right? So, here comes the concept of principal component analysis. So, principal component analysis, or it is abbreviated as PCA, finds a new set of dimensions such that all the dimensions are orthogonal to one another. So they are linearly independent and they are ranked according to the variance of the data that we are making use of. Right? So let us look at the steps. Those are being included in this principal component analysis. So in fact, this PCA, as I stated, is providing new set of dimensions such that all the dimensions are orthogonal to one another. And if the dimensions are orthogonal to one another, that means the features are linearly independent or the features are uncorrelated. Right? And in PCA, these features are ranked according to. We are going to look at this process, how to do that. So this PCA is actually the unsupervised algorithm. Right? So the first step in principal component analysis is to calculate the variance matrix. The variance matrix is denoted as covariance matrix is denoted as sigma in linear algebra. So you must have learned linear algebra in your first and second year of engineering and even prior to that also. So you must be knowing the concept like what we mean by mean of data, variance of data, how to find out covariance matrix, how to find out the eigenvalues and eigenvectors from covariance matrix. So I think you must have gone through all those mathematical concepts, right? So while implementing principal component analysis, the first step that we need to undergo is we need to calculate the covariance matrix of the given data points. Right? Now, once we are having this covariance matrix sigma, then what we are going to do next is using this covariance matrix, we are going to compute the eigenvectors and the corresponding eigenvalues. Right? Now, the third step is we are going to sort the eigenvectors according to their corresponding eigenvalues in decreasing order. Sort the eigenvectors according to their eigenvalues in decreasing order. What next? Suppose I want to pick or I want to transform my space in k dimensions. Then what I'm going to do next is I'm going to choose the first k eigenvectors. First k eigenvectors. Right? And these first k eigenvectors will give me new k dimensions. Right? So, based on the eigenvectors and the respective eigenvalues, we are going to pick up the first k eigenvectors. And these k eigenvectors will form our k dimensions, will form our new space. Right? And once we have formed this new space, then we are going to transform the original n-dimensional data points into these k dimensions. So these are the important steps in principal component analysis. I would suggest you to note down these steps. And we are going to look at with one simple example how it works. Right? Have you understood those steps? What we are going to do, what we have as the input, we are having the input as the data points in n dimensions. What does this mean? This means that every data point is being described with n features. Right? And we want to convert this n-dimensional space into some k-dimensional space. So what we are going to do, we are going to follow certain mathematical steps. Some mathematical treatment we are going to undergo. Right? So the first thing is, whatever data points that we are having, say for example, if we are having such kinds of data points, then what we are going to do, we are going to find out the covariance matrix for all those data points, and we are going to denote this matrix as sigma, covariance matrix. Right? So you must be knowing how to compute this covariance matrix. Studied linear algebra earlier. This simple case, let me tell you. For this simple case of 2 dimensions, we are going to form this covariance matrix, which is having the size 2 by 2. So 2 rows and 2 columns in this covariance matrix. This is a 2-dimensional space. Right? So in 2-dimensional space, I'll be having the covariance matrix with size 2 by 2. So what I'm having here, this element would be variance with respect to x direction. This would be variance with respect to y direction. And here, actually, I am having covariance x comma y. And here I am having covariance x comma y. I'll rewrite it clearly so that you can understand. So in this situation, what I'll be having is this is computed such that I am having here this element is variant with respect to x orientation, here variance with respect to y, here I'll be having covariance x comma y, and here also I am having covariance x comma y. So this is a symmetric matrix, right? So this is how I am going to compute this covariance matrix. Based on this covariance matrix, we are going to compute the eigenvectors and eigenvalues. Right? And once we get these eigenvectors and corresponding eigenvalues, then we are going to arrange those in decreasing order of eigenvalues. And we are going to pick up first k eigenvectors. Right? And these vectors will form our new space with k dimensions. So let me illustrate this with one example. So let us assume that we are having, so in fact this is a broad picture of PCA. We are not going into the mathematical details of all, right? But you should understand the process. So let us assume that we are having a table describing the various instances. So this is actually the instance 1. this is instance 2, this is instance 3, and so on, right? And every instance is being described with 5 features. So one row of this table is one instance or one data point that I am having, and every data point is described with 5 features. Correct? So we are having such kind of a data available with us. Now, let us try to plot this data in 5 dimensions. Now, obviously, it is not really possible to plot this or to visualize this 5-dimensional space. But let us try to do that. So if I try to do this, I may have these 5 dimensions, right? Just imagine that we are having 5 axes in space. Just imagine, okay? And whatever are those values of features x1, x2, x3, x4, x5, we have plotted our data into this 5-dimensional space. Please assume, please visualize that, right? So we are having a 5-dimensional space and quantity features. So somewhere in this space, I'll be having those points plotted, right? So this is a simple, this is not realistic, but this is a simple plot only for just imagining what we are going to do, right? So we have plotted now this data in 5 dimensions. What next we are going to do is, whatever data we are having, the first step that we are going to follow is, we are going to come up with a covariance matrix. So if I am having now this 5 dimensions, 5 features, obviously I'll be having this covariance matrix with the size 5 by 5. Okay, now how we are going to compute this covariance matrix? Just I mentioned earlier, what we are having is, this is the variance with respect to dimension 1, this is the variance with respect to dimension 2, dimension 3, dimension 4, and dimension 5. And the remaining quantities are the covariances actually. So with respect to 2 dimensions. So this is my first dimension and this is my second dimension, third, fourth and fifth. So this quantity is actually describing the covariance between the first, this is first, second, third, fourth and fifth. So this quantity describes covariance between dimension 1 and dimension 2. This describes the covariance between dimension 1 and dimension 3 and so on. And the same quantities are being reflected on the other side of the diagonal, right? And this is how this covariance matrix is symmetric. Right? So this is how we are going to find out this covariance matrix. Now, once we obtain this covariance matrix, by having the mathematical treatment, we are going to compute the eigenvectors and eigenvalues. So these are the eigenvectors and these are the eigenvalues associated. So V1 is the first eigenvector and associated with this V1, we are having this lambda 1, that is my eigenvalue. Right? So from this covariance matrix, we are going to compute this eigenvalues and eigenvectors. Now, what next we are going to do? We are going to arrange those eigenvectors according to the decreasing order of my eigenvalues. So, what we are going to do is we are going to arrange those vectors such that this eigenvalue lambda 1 is highest. This is second highest and so on. Yes, actually the variance describes the spread of data points in that particular orientation. Or direction. What does this mean? Suppose, see, we are having these points in 2 dimensions. Let us assume. Okay, now see here, if I try to find out the projection of these points with respect to this x direction, horizontal vector, right, then I'll be having this projection like this. So the points are spread. The points are spread like this. So every point is being projected like an x orientation. Okay, now this is y orientation. So if I try to project these points on this vector in y orientation, what I will have? I'll be having, this is y orientation, and I'll be having the spread of these points like this. So if we look at this particular figure and the spread of the points with respect to x direction and y direction, then obviously the points are spread more in x direction and the points are spread in the limited space in y direction. So obviously this variance is more. Variance with respect to x orientation is more than y, and will prefer the variance which is more, or the vector which is having more variance, right, or the vector, the data points are spread widely, right. So this is what we mean by variance. Okay, now in covariance matrix we are having those variance values, right, and also this covariance with respect to the respective 2 orientations, right, and based on that we are going to compute these vectors and the associated eigenvalues. Eigenvalues are actually the magnitudes of the vectors, right. So vectors are actually giving us the direction or orientation, and these are the magnitudes, eigenvalues. So what we are going to do is we are going to arrange all those vectors in the decreasing order of those eigenvalues, right. So obviously these upper vectors are more dominant. The upper vectors are more dominant. So if I want to pick up, or I want to convert the 5-dimensional space into 2-dimensional, then what I'll do is I will pick these first 2 vectors, v1 and v2. So this first vector is actually the first principal component. This second vector is the second principal component. So the vector having the highest eigenvalue will be our first principal component. The next eigenvalue, next highest eigenvalue will describe the second principal component, and so on. So if we want to convert the 5-dimensional space into 2 dimensions, then we'll be picking up first 2 principal components. Right? So if we try to project now all this 5-dimensional data with respect to these 2 vectors, then let us assume that we have removed all remaining 3 vectors and we have picked up only 2 principal components or 2 vectors v1 and v2 with the associated eigenvalues lambda 1, lambda 2. So these 2 vectors can be plotted in this space like this. Right? So what I'm going to do is I'm going to project now all these points plotted earlier in 5 dimensions. Those are now being projected to this 2-dimensional space described by these 2 principal components. Right? So these, just imagine that this is a plane, 2-dimensional plane. Right? And these points are earlier plotted in 5 dimensions, and now from those 5 points we'll be having the appropriate projections to this 2-dimensional space. Just imagine. Right? So these points are being projected to the 2-dimensional plane. And this is how now after projection every point will be described by 2 quantities only. So this particular point is being projected here in 2D space like this. So earlier this point was described with 5 features and now this point is being described with 2 features. So similarly every point now is being described with respect to 2 features. Right? And if we try to list out these quantities, feature 1 and feature 2. So this is new feature. So this is a transformed feature. So if we are transforming this feature space, old feature space into new, we'll be getting a small table wherein every instance is being described with 2 features now, W1 and W2. So this instance is being described like this. This instance is being described like this, and so on. Right? So we have reduced the dimensionality. Right? Are you able to understand? Yes? Am I clear? I am just describing you in a broad sense the process. Right? Those who want to revise the concepts, mathematical concepts, you please refer to the respective literature with respect to linear algebra. Practically speaking, if we want to implement this PCA, there are lots of libraries available. Those will help us to find out the covariance matrix, the eigenvalues and eigenvectors, and so on. Right? So as far as implementation is considered, lots of libraries are available directly, those we can use. But what is inside, what is behind that? Behind this, whatever is the mathematics, that is like this, and the process. So you should understand, at least in the broad sense, what is the process behind this principal component analysis. So as I stated, PCA is an unsupervised algorithm, and this PCA is creating the linear combinations of the original features, right? And as I stated earlier, the new features are orthogonal, right? And if the features are orthogonal, this means that these features are uncorrelated, right? And these features we are going to rank according to the variance, right? So the eigenvector according to which we are having more variance, that would be my first principal component. So principal component 1 will explain the most variance in our data set. Principal component 2 will explain the second most variance in our data set, and so on. So whatever is the dimension in which we would like to convert our original space, we need to pick those many principal components, right? And then we need to project our original data in this new dimensions, or the space in with new dimensions, right? And this is how it is possible for us to reduce the dimensionality of our feature set, right? Please remember, here more variance means more spread of the data, and that describes the principal components. So I am summarizing once again. Given the large table, that means given a data set in high dimensions, here the original dimensionality is 5. So what we are going to do is, with respect to this, with 5 dimensions, we are going to come up with the covariance matrix for that, right? So if I am having 5 dimensions, the size of my covariance matrix would be 5 by 5. Okay. Now, based on this covariance matrix, we are going to compute the eigenvectors and the eigenvalues. Right? Next, we are going to arrange the eigenvectors with respect to the decreasing order of the respective eigenvalues. Right? So, whichever is the highest eigenvalue, the respective eigenvector will come first. Now, if we want to convert the higher dimensional space into the lower dimensions, then whatever is the required dimensionality, right? Those many vectors we are going to pick. So whenever we are saying these are the vectors arranged according to the decreasing order of the respective eigenvalues, the first such vector is our first principal component. The second such vector is our second principal component, and so on. So whatever is the required dimensionality as the output space, we are going to pick those many principal components, or in other words, we may pick some threshold with respect to this eigenvalue, and all the principal components for which the eigenvalue is greater than that threshold, we are going to pick all those principal components, and that will describe our output dimensionality, right? So once we have picked up all such principal components, those principal components are nothing but the vectors, right? And these vectors are now describing our new space. So in this case, these two vectors we have selected. So two principal components we have selected, and this is how we are getting this two-dimensional space described by these two principal components. So this is my principal component 1 and this is my principal component 2. So we are having now this plane, two-dimensional plane described by these two vectors. So the next step is we need to project the original data points from 5 dimensions to 2 dimensions. So we'll be having some transformation function here. So by making use of that transformation function, we are going to transform the points, right, from one space to another space. So using this transformation function, we are coming up with this two-dimensional plot, wherein old point that was described with 5 dimensions is now described with 2 dimensions only, right? So the corresponding feature vectors, new feature vectors with respect to all the data points are listed now in this table. So if we look at these two tables, earlier we had 5 dimensions, now we are having only 2 dimensions. So we are reducing the number of dimensions, right? And rest of the things. So now with this transformed feature vectors, we are going to implement our machine learning algorithm, right? So this is broadly the principal component analysis procedure. Fine. So let's conclude today. Thank you.